Morning, guys. Just let us know when you arrive and who's here, just so I know who I'm talking to. I think there's a couple of people who just logged on. And let me know if the sound is okay, because I have a new mic set up. Morning, Dry. Morning, Hannah. That's good. Hopefully, there'll be less echoey, less kind of static, and a bit of a clearer sound. So good. I'll just give you a couple more minutes just to see who else is going to log on. As of now, I think we've got 2 or 3 people. Hello, hello. Is that better? Okay, cool. Cheers, guys. I'm not sure what happened there. Okay, so I'm not sure where I lost you, but I'll just go back through what I was mentioning. So our first 4 planets are referred to as gaseous planets. Rocky planets. So these planets here are going to be our rocky planets. Again, they'll never ask you this, but they will probably refer to it in a question that rocky planets are here, and you may trip over that and think, kind of, what is a rocky planet? But all they're referring to is the first 4 planets. And gaseous planets are generally larger because obviously gas can take up more volume. So these are gaseous planets. We fundamentally don't actually know what makes up the kind of core and the center of these, but we just know that they're largely gaseous in their makeup. Pluto, you do need to know that it's referred to as a dwarf planet, and it kind of sits out here, and it's just to do with size. That's all it is. And it's as time goes on, the classification of planets and stars and universes will probably change. And then we've got this belt, hundreds and thousands of miles away. So let's just kind of clarify some sizes, because we kind of band these terms around like solar system and universe and galaxies, and we may not actually know what we are kind of talking about in that sense. So let's move this. Okay, so when we actually refer to a solar system, what we actually mean by that is, so a solar system is the smallest. So let's change color. So it is the smallest of our classification system. And there are 3, we have a solar system, we have a galaxy, and then we've got the universe. But our solar system will consist, or make up by a star, and then there's objects and planets orbit around it. And these are bound. These plants. These planets are bound then in the orbit by a gravitational pull. And obviously, sorry, not obviously, but these will have their own moons. May have moons. Okay, so the planets will have their moons that will orbit around the planet, and then the whole planet will move around the sun. Then you've got galaxies. And this is effectively a system of solar systems. Okay, so you do need to be aware. Our galaxy is the Milky Way. And generally, like galaxies or the solar systems within galaxies are separated by huge, incomprehensible amount of space. And even in our own galaxy, so the Milky Way galaxy, there's this rough kind of estimate that there's about 200 billion different stars, and they're obviously going to have their own planets that are orbiting, and they're going to be separated by thousands of light years away. And it is thought that the galaxies orbit around a massive black hole that generally provides, well, it's not even massive, well, it is massive, but it's this vast, dense object that we orbit around, and it's thought then that our solar system takes about 200 to 250 million years to actually orbit around the Milky Way galaxy, and then that galaxy's orbiting around this massive black hole, which in itself will take a period of time. And then our last one is the universe. And this is obviously the largest. Let's go back to red. And now it's everything. It includes absolutely. Plus solar systems. And that's, again, as we say, it's incomprehensible, the distance. We're talking about millions of light years, where a light year is the distance equals a distance light travels in a year. Okay, so it's nothing to do with speed, but it has everything to do with distance. So this is, again, a nice number to be aware of is light will travel at 3.0 times 10 to the 8th meters per second. So it's traveling huge. It's 300 million meters per second, and then you just take that up from a year, and that's how far things are away. So when I told you that our solar system, or it takes, well, one black hole that they're hypothesizing is about 55 million light years in diameter. That's 55 million years that light is traveling at this speed. So that's an incredible distance. Huge. It's ridiculous. So yeah, but that's so when we're talking about our solar system, we are actually only referring to this in respect to the universe, this tiny kind of small collection of objects orbiting this star. So that kind of leads us on to things orbiting. So kind of, why do things orbit around? And to think of this is, why does this bucket of water stay, when you swing it around, it stays in motion? So if I kind of tracked this, apologies for the kind of rough arc. Oh, that was going so well. But if we all swing a bucket, why does it? I'm actually going to now ask you, so type in your response, please. Why does this bucket stay in orbit? Why does it actually move around in this circular path? Yeah, let's leave it there. All right, so there must be something, if we think of the angle that it's going, let's think of it in reverse. If I let go of this bucket is actually going to fly off in this direction. If I let go of it, we all know that if you swing something around, you let go, it flies off in this direction. So there must be something. Actually, if we now look at it, if that's one component of its vector, so the vector isn't here, but its resultant vector is in this direction, to get there must be this vertical component, which actually is pulling it in this direction. And then that's going to be the tension of the string. So it's the tension of the string or the rope that's actually holding this or pulling it towards the center. It wants to move off in this direction, so it's constantly just going in this arc. So if I go off here, it will have a component over here, and then it's got its component over here. So the tension of the string is over here. So it's actually being accelerated inwards towards the center. It's been trying to be pulled in towards the center, but it also has this velocity or this speed going off in this direction. So what they might ask you is, or there's this concept then that we could say that this bucket is in this state of constant acceleration. And acceleration then suggests that it's constantly getting faster. But actually, it's to do with its velocity. So while its speed doesn't change, it doesn't change. Its direction does. So actually that implies then it's in a change of velocity. And now if I go back to my term here, acceleration, we're in this constant state, so I'm always accelerating in a new direction, because actually if we look at our formula for acceleration, acceleration then is the change in velocity over time. So my velocity, because my direction is always changing, my velocity is changing, and in a period of time, my velocity is changing in a period of time, so I'm always in a state of acceleration. Okay, so it sometimes pops up that they say, how can velocity change of a planet? How does the velocity of the Earth change when the speed never changes? And the reason being is because its direction, velocity is a vector, so that's important to know. So it has size plus direction. So if its direction is changing, that means then that this velocity is changing. So then, if the tension of the string is keeping our bucket in orbit, what is holding the Earth then in orbit? Does anyone know? So I've just seen your questions. Hopefully, Jerome, I've kind of cleared up your question or your statement. Tom, so the acceleration is not constant. The bucket is in a constant state of acceleration. Yeah, spot on. Because acceleration is a vector or is a vector, you can say that it's constantly accelerating in a new direction. And it applies if you go around, it's the same thing as if you go round a roundabout and you try and maintain, or your parents try and maintain the same speed, because you are changing direction, you are accelerating in a new direction. So you are in this constant state of acceleration, but the value is not constant. Hopefully that clears that up. So, what's holding the Earth together, or what's pulling the Earth? So if we have the sun in the middle and we have the Earth over here, and the Earth does some orbit like this, the sun obviously has this massive mass, which is something that I'm going to have a rough, I think it's 2.0 times 10 to the 30 kilograms, and the Earth has something like 6.0 times 10 to the 24 kilograms. You know, so it's huge in comparison, even though you got to remember that this is in a magnitude of 6 times, or by 6 times bigger. Anything with mass, we then say that there is this gravitational pull. And it's that gravitational attraction that is now keeping this or our Earth in orbit. You know, if that sun wasn't there, then we'd fly it off in this direction. So it's the force due to the attraction of gravity that is keeping us in this bound orbit state. And that's why we call it, or you may hear the term, centripetal force. Because this means, when you actually look at the word, when you look at the Latin, this means center, and this means seeking. So it's a center seeking force. You know, it's acting towards the center. But what you need to take away. So then now if we look at the Earth in itself, and we can look at, say, other planets as well, we can now look at the Earth, and the Earth has the Moon, which again will orbit around the Earth. And we will refer to the Moon, even though we call it the Moon, its technical term is, or any moon in that respect, is known as a satellite. And importantly, it is a natural satellite. And then you actually have artificial satellites. Now these generally will include any of the satellites that we can think of. You know, I suppose it's more abstract to think that the Moon is a satellite, but you're probably more comfortable with thinking of GPS satellites, weather satellites, communications satellites, and they're what they're going to refer to in your exam. And there's huge amounts of uses of satellites. And normally what you're going to do is you're going to find that these satellites have a smaller orbit, so they're a little bit closer to Earth. So let's just say that this is I don't know, a telephone satellite. So when you're making a mobile phone, you know, we're a communication satellite, and it travels in this orbit. Obviously, apologies, these should be circular orbits. You do get ellipse orbits of, say, comets orbiting around the sun, or orbiting, they'll orbit around the sun, and they'll be more ellipse in nature. But when we look at these satellites, and we look at, say, the artificial one first, can you please tell me, or can you compare, please, and just put your answers in the comment section? What is the difference then between, say, these two speeds? So what is the difference between, say, satellite 1 and satellite 2, which is our moon? And which one will orbit the Earth quicker? So answers in the comment section, please. What is the difference in velocities or in speeds between our artificial satellites, which is closer to the Earth, and our natural satellite, the moon, which is further away from the Earth? Okay, so Jerome's answer is our natural satellite number 2 is going to be slower, so we'll have a slower velocity than satellite 1 because it has a less gravitational pull. Okay, so why is that, Jerome? Why will it have a less gravitational pull? Fundamentally, Jerome's right. Yeah, this will be slower. So this would be slower. It will have a longer or bigger, what we call orbital time. So effectively a month. And this one will be quicker. And it will have a shorter, this may have like a day or hourly orbit. And it does come down to a gravitational pull. Right, so the key thing, yeah, nice one, Harrison. The key thing there in your answer is that it's actually closer. So the distance between, say, the center of the Earth, which is where the gravitational pull acts from, the distance is smaller. So it's this distance here that is actually really important. So the further away that you get, the longer it's going to take. Yeah, Harrison, great link to electrons. That's it. Yeah, the closer they are, yeah, fantastic. Yeah, it's a really good cross link. Yeah. So if they are closer, that centripetal force is increasing. So then their speed will actually increase, the orbital time will increase. So height is very important. We could also talk about the mass. I've rarely seen it come up in GCSE questions, but the bigger things are there is that can affect our gravitational pull as well. So if we kind of have a little look at some numbers in our system, so here is our distances. So over here we've got the sun. From here, and these are our first kind of 4 planets really, so 1, 2, 3, 4, and then we start to get our gaseous planets all the way out here. So our distance, Neptune, is huge, and these are all kilometers, so these are not even meters. So these numbers are still massive numbers, and they're in kilometers. So they're huge distances away. And then now when you talk about velocities, you can actually see that Mercury has this velocity of 47 kilometers per second. So that's 47,000 meters per second that it's traveling. And then the Earth's orbit is effectively 30,000 meters per second that is traveling. So, even just as I was saying that, think about actually how fast we've actually traveled. We've probably done a couple of 100,000 kilometers just as I've been talking, and as we go further away, orbital velocities decrease. So as we move down here, orbital decrease. If this was an exam question, they may give you this data, obviously in not this nice pretty format, but they may give you this data and ask you to spot any trends or describe the trends. Be very, very careful then, because what you also may have to include is include data. You would have 1 low value plus 1 high value, just to support your claim that as you get further away from the sun, or you get further away from the center of this gravitational pull, velocity is decreasing. And then you may ask to compare data. They may give you the distances of the planet and then say compare the distances and orbital velocities, and then again you would say the closer you are, the bigger the velocity, and then quote data, and then if they ask you to explain this, then that's when you'd link it back to the closer you are to the sun, the stronger the gravitational pull, thus your velocity will increase. Galaxies, this is just quite cool. There's nothing really to talk about, but this is the Hubble telescope, or this is one of the very famous discoveries that we had, that this image in theory was, or kind of in scale, is if you put your thumb up an arm distance away, the image over here, these are all galaxies that we can see inside the Milky Way galaxy. It's like ridiculous. Every single dot you can see, even the smallest dot that you can see, is due to a galaxy. Now, this will kind of lead on when we start talking about a couple of things in a sec. But we refer to anything really that is luminous. Okay, so it gives off light by itself. A star is luminous because it's giving out energy in the form of light. So when hydrogen are fusing together, they are expelling light or expelling energy as light. Thus, they are luminous. If something is illuminous, it is reflecting light. So, for instance, the moon is luminous because it's reflecting the sun's light, whereas the sun is a luminous object because it's generating its own light. Harrison's question: what is the mnemonic to remember the order of the planets? It's just good to know, I suppose. This is the one that I was taught in primary school. It still holds valid today. So if I do my very easy method just speeds up naming planets, and forget the P now because that was Pluto. So my very easy method just speeds up naming planets Pluto. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then this is a picture of our Milky Way galaxy. This strand here is our Milky Way galaxy. I thought they were just cool pictures to have a look at. Okay, so one thing that I didn't actually, one thing I forgot to talk about in here is the type of wave that we use to talk to satellites, and we use microwaves. So the type of wave that we're going to use for these is microwaves. It pops up in P6, so still paper 2, but they may tie that into this question. And why do we use microwaves? Because it can pass through the atmosphere. So radio waves cannot pass through the Earth's atmosphere. It bounces off the Earth's atmosphere, whereas microwaves can penetrate through the atmosphere, get to the satellite, and then come back down. So that's why we can use, or in your mobile phone, we use microwaves as communication, and we can communicate all over the world pretty instantaneously due to the fact that microwaves can penetrate through the atmosphere. Radio waves, that's why we listen to long wave, because long wave is actually bouncing off the Earth's atmosphere and it's reflecting off the Earth's atmosphere. But sometimes I've seen that pop up every now and again. It throws often a lot of students out. So let's talk about the origin of the universe. I suppose that's probably a good place to talk about, and then we'll go on to the life cycle of the star. So the origin of the universe, or what scientists are now the most kind of accepted theory to explain the origin of the universe, is the Big Bang. So the Big Bang is just a theory. A theory is very, very different to a law. A theory is what the science supports best at the moment. A theory can change. So a theory can change. It is based on science. It is okay, whereas a law cannot change. Like the law of gravity. I'll stick my neck out, I suppose. You know, it's a law. It will never change. It's been proven on belief or without doubt that there is a law of gravity. There is a law of conservation of energy. It must happen. Whereas, you know, we used to think that the Earth was the center of the universe, and due to new evidence. So this is what they're going to start on the space topic. This is really where the questions come that I think most students trip over, is when they start talking to you about evidence and theories and how models support things. So we found new evidence to support a theory of the Big Bang. Now, really good evidence, sometimes what they ask you is, why might someone peer review something? You know, peer reviewing is asking or getting other scientists, other peers, or other scientists, whatever the field they're in, asking other peers to critique their work. Okay, and every journal that someone will write, they'll publish this journal, which basically is a lab report, and then they'll have their conclusion and they'll put it out to the world, and all these scientists will look at it and then try and critique it and find holes and spot flaws. And the more people that review it and the more people that critique it, and if they can't find any flaws in this, then they say that this is a very good theory. So we ask people to peer review things to strengthen a theory. Yeah, so just be very careful of the terminology you use. Often evidence, or say the big, so evidence supports. And that's the key word, it supports a theory. Okay, it doesn't prove it, nothing is proved, it just supports the theory. So everything that we have, all the evidence that we have, like redshift, taking data or analyzing velocities of different galaxies, everything that we have at the moment all supports this idea, this theory of the Big Bang. So kind of what actually is the theory of the Big Bang? The theory of the Big Bang is the universe, so everything, so the largest thing we measure, the universe started in one place. Okay, or you could say a single point. There was this massive explosion, and from that the universe has continued to expand. So so the universe is now expanding. Oh, that should be capital letter. So that's your 3 bullet points that you would say the theory of the Big Bang. It started one single point, and who knows what started this huge explosion. Maybe that can be your career. You go off and you solve that problem, you do that, you become famous, like world famous. This huge explosion, and then now the Earth is expanding. The universe is expanding. And what theory do we have for that that helps support this? That is the theory of redshift. So what is redshift? And again, students tend to kind of overcomplicate this. But you're rarely ever asked to give the definition of redshift. They'll describe the theory and then ask you, what is this concept? But it is just as galaxies, I suppose I could stay in red if we're talking about redshift. or object. From the observer. The wavelength increases. And that's fundamentally it. And how does it actually prove that the Big Bang, light from distant galaxies are moving or kind of shifting towards the red end of the spectrum? So if we have a spectrum over here and we have red on this end, apologies, I've only got kind of say blue, and blue is here, so this is a spectrum that we're going to go through. Have I got purple? No, purple will be over here. And then you're going to have green somewhere here, let's just say. Have I got yellow? So as a galaxy is, say, at this point, so here is the observer, here is Earth, we're making our observations, and then we have some unknown planet here, so we'll just call this planet P. I don't know, and in year 2019 we make this observation and a light is emitted from here, and it travels all the way to us. Let's make that a little bit better. It travels all the way to us, and it has some wavelength, okay? And in 2020, this is obviously not to scale in the least. The planet P now has moved in respect to the Earth. So this is now 2020. This might take hundreds of years, 10 to 20 of years to even move this scale. This wavelength now has actually increased. So the light now we're starting to receive is more towards this red spectrum. Okay, so we say now that the wavelength has increased and it has been red shifted. Okay, so that's all it is just as galaxies move away, the wavelength increases, and it moves towards this. So this is obviously red has a long wavelength, and blue, violet has a very short wavelength. They'll never ask you this in the exam, but if the planet's moving this way, then in respect to us, so obviously this has gone this way, if it starts to move towards us, we would then say it's been blue shifted. Harrison, yeah, exactly that. It is just a massive, and it's huge. It was actually discovered by someone writing their thesis. It was discovered by Edwin Hubble, but it is just a theory that supports the universe is expanding, because we have planets that we were detecting one type of spectrum, and now we are detecting from the same planet the waves or the light that we are detecting, which is just energy, we are detecting now is moving towards the red end of the spectrum. The wavelength is increasing. It is being red shifted. It's not saying that it is red. It is just that the wavelength of that light is increasing. Thus, we are saying it is red shifted. That's all that is happening. So what does, if like Harrison just said, this supports the Big Bang Theory, and what we're actually found is it's really weird. We shouldn't have seen this. That actually, what we call recessional speed. So again, they'll rarely ever seen this question come up saying define recession speed, but recession speed is the rate at which they are moving away from us, and this is generally an object in space is moving away. Okay, so what that actually means is if I draw in some other planets, so let's just say I'll make up the planets now. So planet A and B are here. The recessional speed of P, because P is so far away from our Earth, this has a greater recessional speed. This is moving away faster than it should. It should actually be the other way around. These guys are actually moving faster away than A to E. So this maybe expanding and kind of moving away from us at a particular speed, but P is moving away from us even faster than these guys are. And that shouldn't happen, and we can't explain why. Well, we have this idea then of dark matter, but we don't really know what that is, and I'll talk about that in a sec. No. Actually, I don't know, Harrison. That's a good question. Harrison's question is there a speed for when it's moving towards us? I imagine the recessional speed there might be negative. If it's in the negative sense, then it's moving towards us. But I don't know, actually. That's a good question. So let's touch on that dark matter now, and then I'll come on to the life cycle of the star. Right. Now, they'll never, I don't know how they're going to refer to dark matter. I didn't see it. There wasn't a question on it in the 2018 paper. It's very, very vague in the spec. It's just briefly mentioned. So normally they tell you if is because it does not interact with light. It doesn't actually interact with anything on the electromagnetic spectrum. But the reason why we actually know that this thing exists is, one, because mathematically we can prove that there is something there, but the mass of all the galaxies and all the stars, they don't account for the speeds that they're at. They don't account for the gravitational pull. So there must be this other thing pulling things together. Because anything with mass has a gravitational pull, but when we look into space, we can see the effects of gravity. We can see things pulling on things. But as I said, the mass of all the stars and all the galaxies, it doesn't add up. and we have just called this thing dark matter. We fundamentally don't know what it is. We don't know that much about it. We just know that there is this thing being created, dark matter, which is causing the expansion of the universe. But we just know it's dark matter. The other thing that we have is this dark energy, and dark energies. Dark matter. Apologies, I got that around the wrong way. Because dark matter has mass, so it has mass. You're never going to be asked too much about it. I just want to kind of give context. So it has mass, and if it has mass, it has a gravitational pull. Okay, so that is trying to actually constrict the universe. But there is this other thing called dark energy. Okay, so dark energy, because again, it doesn't actually interact with anything, but the universe is expanding. It's expanding at the rate faster than light. We don't know why it's causing it, but obviously, if the the universe is expanding, that means there is work being put in. That means there is energy being put into expanding the universe. We don't actually know what that is. We call it dark energy. But once we find it, we'll probably change the name. One thing to think about, though, is space is expanding between universes. Between galaxies. So physically, you are not expanding. It is the space. There is fundamentally been matter being created in between galaxies and pushing out, and causing the universe to expand. Really complex stuff. So again, if you fancy earning a lot of money, getting your name into history, this is something to kind of go off and investigate and spend your life researching. But let's have a look at the life cycle of a star, which is often where they're going to get your 6 markers and 4 mark questions. So life cycle of a star, where does it all begin? All begins with bits of dust we call a nebula. And this is just clouds of gas which fundamentally collapse, or they kind of come together due to their own mass. So again, anything with mass has gravity, so they eventually become they start to pull together, they get closer and closer together, and then they start to form what's known as a protostar, which is just a baby star. So in here, what actually happens is fusion starts to begin. So fusion, so of hydrogen and helium, prevents further collapsing. So obviously these are, you could term it, these are collapsing in on each other, but the fact that there is now fusion, creation of elements, so there's going to be some pressure, prevents further collapse. And energy now, due to fusion, is being transferred into light. So there is luminous light being given off. Now, this is where, so all stars, no matter what size they are, they're going to go through here, okay? But then we come to something called the main sequence star, So this is the most stable form. So this is where our current star is at the moment, but due to fusion, there is an equilibrium between the gravitational collapse of a star and the expansion. So the outwards pressure is equal to the inwards. Gravitational pull. And this is all due to the fusion reactions going on. Of a star. Okay, so that's where we are at the moment in terms of our star, and this is where it forks, this is where it branches off. Now, the reason why it does that is if I start down here, it might, I can explain the other side. So this is stars same size as our sun. I should say same mass as our sun. We are then going to go off and form a red giant. We'll start to cool down and we'll form a white dwarf. And then we'll go into a black dwarf. Okay, and these are all just terms of stars. A red giant star, white dwarf star, and a black dwarf star. So, what is actually happening in this red giant? So, hydrogen has basically ran out. So, hydrogen has run out. So, fusion stops. And the star starts to suddenly collapse in on itself. And then we start to actually form this white dwarf. Okay, so a white dwarf is just a smaller star. It's no longer fusing, and the outer layers are thrown out. So basically, all the elements, all the debris, is thrown out into space, and you are just left with this core. But the reason why it's called white is because it's still very hot. It's still emitting light. So there's no fusion happening. But it's still emitting light. Okay, because it's still very hot, so it still has lots of energy to emit, and this is just cooling down. Okay. Not emitting light. Or, yeah. It's not emitting as much light, really. So, when this kind of goes through this, so there's, sorry, through the white dwarf, and there's this kind of the outer layers of the star being kind of thrown out into space, that's effectively these clouds of gas. This is where it's all come from. So it's fundamentally gone through a version of a supernova, and it emits this gas. Now, if huge amounts of this gas gets together, it still forms a protostar, but it forms a bigger protostar. And then it goes into a main sequence star, but it's a miles bigger main sequence star. Let me just get rid of this. So then that's why we now go down this path. So this has a miles bigger mass than our sun. So these stars are much more mass. Okay, because it all started with more gas forming, more clouds of gas forming to form a bigger nebula, which then was a bigger protostar, which formed a bigger main sequence star, and then it kind of goes down into this red supergiant. And this red supergiant, again, it goes through the exact same process as a red giant. It is just at a bigger scale. And what's kind of more interesting to know is generally it'll burn brighter. So fusion happens quicker. You won't ever be asked this. But this explains why sometimes you see blue stars, because the fusion is happening quicker and there's more energy being emitted, and the intensity of all of this is miles greater than a red giant. We then start to see blue stars, and the shift through here is a lot quicker than if it's the same size as our star. Then we go into this supernova. Oh. And this is just a huge explosion, and depending on the mass, you're either going to form a neutron star or a black hole. No, these were just pretty much theoretical until we had the recent discovery, the recent image of a black hole. But we now have photographic evidence that these actually exist. But depending on how quick the rapid contraction is, what you actually have is, you know, that there's obviously no fusion going on, so there's no more elements being created, but what you do have is you have the collapse of all the protons, all the electrons that was in the atoms, and you just have a huge collections of neutrons, and they are absolutely massive. So the gravitational pull is so great that you form a huge bundle of neutrons, and this causes all the elements above iron. Okay, so that's actually quite important to know that when we're going through this main sequence star, this forms elements up to iron. Anything above iron actually only happens in a supernova. And all our elements, like iron is the most stable atom that we have, and when you kind of go on to A-level physics, we start to explain why iron is so stable. But fundamentally, anything above iron, gold, cobalt, etc., is all formed through a supernova. So I appreciate that's about an hour. or that's just over an hour that we've been going. So I appreciate I'm over the time that I suggested that we would be going for. So I appreciate, Charlie, like, you're heading off, no problem. Glad you enjoyed it. I have a couple of exam questions here that we can go through. But I think I'm going to just leave with this one because this was probably this was the hardest question and the most abstract. So let's give this one just a quick go. It is, let me just double check. Describe what will happen. I think this is a 4-mark question. Indeed, yeah, this is a 4-mark question. So pause the video, give it a quick go. It's 4 marks, so there's a nice confusing diagram there that we've got to think of. There's lots of information, so give it a pause, have a quick go, and then I'll see you once you've unpaused it. Right, so let's have a quick look. So it's 4 marks. The 4 and 5 marks are generally the hardest questions on the paper. So these are your level 8s and your level 9s. So at different points in a life cycle, stars change from one group to another. Describe. So we don't have to explain anything. We've just got to say what is happening. So that means what is happening. To the sun between it leaving the main sequence group. Okay, so whereas the sun is here, so this is just a group of stars that is in the main sequence. Okay, so it's not an actual star itself. There's the star we're talking about, and it becomes a white dwarf. And key thing, you've got to use information from the diagram. So let's have a look. First thing first, let's have a look at what the graph actually means. So on the y-axis, I've got increasing relative luminosity. So in relative to, I imagine, the sun, luminosity is getting bigger as it goes up here. So luminosity, so light given off. So this is light emitting. So more light is being emitted by the supergiants, which makes complete sense. They're bigger, they have more atoms, more light being given off. Down here is decreasing temperatures. So that means then that through here, I imagine then that it decreases this way. So temperature, so T, gets smaller. The temperature is getting smaller. So this is high over here, this is low over here, which makes sense because a red supergiant or supergiants surely should have more surface temperature than a white dwarf. So we need to describe. So we're going from this position here to this position here. So first things first, we know that from our previous diagram that our sun is in a main sequence star. So then it first must actually change. It is going to go into a red giant. So that's going to be our first thing, because we can't just say it goes from a sun straight to a white dwarf, because that doesn't actually happen. So the sun to a red giant. Then it's going to go from a red giant. Remember, we're just describing, and it's understanding that this is fundamentally just saying that diagram that we just had, it is just asking for that left hand side of that flowchart. Then it goes, oh sorry, you should say rather than it, that's a very confusing term, the sun will go from a red giant to a white dwarf. Okay, so there's my 2 points. I've explained how I've got from here to here, because that's what it's asking me to do. Goes from a sun from the main sequence group and becomes a white dwarf. I've explained that left channel. Now I've got to use information from my diagram to also say what's going on. So I've got to say then that when it changes, when the sun goes from a main sequence star to a red giant, the luminosity will change. So when the sun changes, sun changes to, I should say, changes from a main sequence to a red giant. So I've gone from here to here. The temperature has decreased. I've gone from here to here, so T has gone down, but luminosity has increased. So surface temperature, I'm just going to use the term T, has decreased. Again, we don't have to say, you can use the word smaller, plus relative. I'm just going to quote the axes, so you just use whatever axes, so relative has gone up. So my 4th point is going to go up here. And then now I've gone from here, so then now I'm going to go from here back down to here. So my temperature is getting up because we said that T is getting smaller, so then my arrow is telling me what's happening, so it's a reverse axis. So my white dwarf, my surface temperature has gone up, but my luminous has gone down. So let's write this in a different color. From red giant to white dwarf. Surface temp decreases. Oh, sorry, increases. Which makes sense because red is a longer wavelength. If it's got a longer wavelength, it must have lower amounts of energy. White, when it's white hot, it's giving off loads of energy, so it must have a very, very short wavelength. But relative luminosity decreases. Okay, so hopefully you can start to see the when we use graphs, you know, they're just a way of telling a story, and it's making sure we get maximum amount of information from our graph and ensuring we've read that key statement that says use the information from the graph or use data. You must use it to get your marks. And you know, and again, it's just saying what you see, and it's just being able to pick the information out. But those 4 bullet points would have got yourself 4 marks. Hopefully that's been useful to you guys. Apologies, it's gone on a bit longer than I had planned, but we'll pick up the extra questions on Monday when I see you guys again. So hopefully you'll have yourself a great weekend. Any issues with space or with revision, please just pop by in the lab and give me a shout. But from myself, have yourself a great weekend, and I'll see you guys Monday.